Chapter 2, Data Models and Query Languages. So in this chapter, we'll particularly compare the relational model, the document model, and a few graph-based data models. We will also look at various query languages and compare their use cases. The best known data model today is probably SQL, where data is organized into relations which are called tables, and each relation is an unordered collection of tuples, which are called rows in SQL. And the latest attempt to overthrow the relational model's dominance is of NoSQL. So the name NoSQL doesn't actually refer to any particular technology. It was originally intended simply as a catchy Twitter hashtag for a meetup on open source distributed non-relational databases in 2009. Now, there are several driving forces behind the adoption of NoSQL databases, and some of them are a need for greater scalability than relational databases can easily achieve, a widespread preference for free and open source software over commercial database products, specialized query operations that are not well supported by the relational model, and frustration with the restrictiveness of relational schemas and a desire for a more dynamic and expressive data model. So, most application development today is done in object-oriented programming languages, which leads to a common criticism of the SQL data model. So if the data is stored in relational tables, an awkward translation layer is required between the objects in the application code and the database models of tables, rows, and columns. And this disconnection between the models is called impedance mismatch. Now, to cope with this, object-related mapping comes into picture. The ORM frameworks like Active Record and Hibernate reduce the boilerplate code required for this translation layer. Let's see that how a resume could be expressed in a relational schema. So the profile as a whole can be identified by a unique identifier, which is the user ID. And fields like first name and last name appear exactly once per user, so they can be modeled as columns on the user's table. However, most people have had more than one job in their career, which we call positions here. And similarly, for education and contact information as well, they might have more than one value per user. So you can represent this data in a traditional SQL model, which is the most common normalized representation. And here you can put positions, education, and contact information in separate tables and put a foreign key reference to the user's table, which would be this. Now, another option to represent this data where, like in case of a resume, which is basically a self-contained document, another better option to represent this data would be a JSON representation. So if you see here, all of the unique entities can be represented like this. And for the entities which are repetitive like positions, they can be represented like this. Similarly for education, contact information, and so on. Now, some developers feel that the JSON model reduces the impedance mismatch between the application code and the storage layer. The JSON representation has better locality than the multi-table schema. If you want to fetch a profile in the relational example, you need to either perform multiple queries or perform a messy multi-way join between the user's table and its subordinates tables. In the JSON representation, all the relevant information is in one place and one query is sufficient. So many to one and many to many relationships. Now in the above example, region ID and industry ID are given as IDs, not as plain strings like Greater Seattle area. Why? So whether you store an ID or a string is a question of duplication. When you use an ID, The information that is meaningful to humans is stored in only one place, and everything that refers to it uses an ID. Now, when you store the text directly, you're duplicating the human meaningful information in every record that uses it. And anything that is meaningful to humans may need to change sometime in future. And if that information is duplicated, all the redundant copies need to be updated. This incurs write overheads and risks inconsistencies. Removing such duplication is the key idea behind normalization in databases. Now, one thing to note here is that in relational databases, joins are easy, whereas the support for joins is weak in document databases. Document databases in NoSQL reopened a much older debate on how to represent many-to-many relationships in joins. The most popular database for business data processing in the 1970s was IBM's Informant Management System, IMS. The IMS used a data model called hierarchical model, which has remarkable similarities to the JSON model used by document databases. It represented all data as a tree of records nested within records. Like document databases, IMS worked well for one-to-many relationships, but it made many-to-many relationships difficult and did not support joins. So, two of the most prominent solutions proposed to solve the limitations of hierarchical model were relational model and the network model. Now, let's take a look at the network model. The network model was standardized by a committee called the Conference on Data Systems Languages, hence the codicil model. The codicil model was generalization of the hierarchical model. Now, in the tree structure of hierarchical models, every node has exactly one parent, whereas in the network model, a record could have multiple parents. This allowed many-to-one and many-to-many relationships to be modeled. Now, the links between records were not foreign keys, but more like pointers in a programming language. So, the only way of accessing a record was to follow a path from a route along these chains of links. And this was called an access path. So, in the simplest case, an access path could be like the traversal of a linked list. But in case of many-to-many relationships, several paths can lead to the same record, and the programmer had to keep track of these different access paths. So, a query in codicil was performed by moving a cursor through the database by iterating over lists and following access paths. So, with both the hierarchical and network model, if you didn't have a path to the data you wanted, you were in a difficult situation. Relational model. So, the relational model was to lay out all the data in the open. A relation is simply a collection of tuples, and that's it. So, in a relational database, the query optimizer automatically decides which parts of the query to execute in which order and which indexes to use. You only need to build a query optimizer once, and then all the applications that use the database can benefit from it. Now let's compare the above discussed models with document databases. So, document databases reverted back to the hierarchical model in one aspect, storing nested records within their parents instead of separate table. However, when it comes to representing many-to-one and many-to-many relationships, relational and document models are not fundamentally different. In both the cases, the related item is referenced by a unique identifier, which is called foreign key in the relational model and a document reference in the document model. Schema flexibility in the document model. Most document databases and the JSON support in relational databases do not enforce schema on the data in the documents. No schema means that arbitrary keys and values can be added to a document, and when reading, clients have no guarantees as to what fields the documents may contain. Document databases are sometimes called schemaless, but that's misleading as the code that reads the data usually assumes some kind of structure. That is, there is an implicit schema, but it is not enforced by the database. A more accurate term is schema on read. where the structure of the data is implicit and only interpreted when the data is read, in contrast with schema on write, which is the traditional approach of relational databases, where the schema is explicit and the database ensures all written data conforms to it. Schema on read is similar to dynamic type checking in programming languages, whereas schema on write is similar to static type checking. The difference between the approaches is particularly noticeable in situations where an application wants to change the format of its data. For example, let's say you are currently storing each user's full name in one field, and you instead want to store the first name and the last name separately. So to make this change, in case of document database, you would just start writing documents with the new fields and have code in the application to deal with the two formats. Whereas in case of statically typed database, that is relational databases, you would typically perform a migration. So these are the queries which you would perform in PostgreSQL and MySQL. So first you would perform an alter table command and then update. So most relational databases execute the alter table statement in a few milliseconds. MySQL is a notable exception. It copies the entire table on alter table, which can mean minutes or even hours of downtime when altering a large table. The schema on read approach is advantageous if the items in the collection don't all have the same structure for some reason. For example, there are many different types of objects and it is not practical to put each type of object in its own table. Or, the structure of the data is determined by external systems over which you have no control and which may change at any time. Data locality for queries. A document is usually stored as a single continuous string encoded as JSON, XML, or a binary variant thereof. If your application often needs to access the entire document, there is a performance advantage to this storage locality. If your data is split across multiple tables, multiple index lookups are required to retrieve it all, which may require more disk seeks and take more time. The locality advantage only applies if you need large parts of the document at the same time. The database typically needs to load the entire document even if you access only a small portion of it, which can be wasteful on large documents. Hence, it is recommended that you keep documents fairly small and avoid writes that increase the size of a document. For example, Google's Spanner database offers the same locality by interleaving off tables within a parent table. Oracle allows the same using a feature called multi-table index cluster tables. The column family concept in the big table data model has a similar purpose of managing locality. Convergence of document and relational databases. It seems that relational and document databases are becoming more similar over time, and that's a good thing. The data models complement each other. PostgreSQL since version 9.3, MySQL since version 5.7, and IBM DB2 since version 10.5 also have a similar level of support for JSON documents. On the document database side, RethinkDB supports relational-like joins in its query language, and some MongoDB drivers automatically resolve database references, effectively performing a client-side join. Although this is likely to be slower than a join performed in the database since it requires additional network round trips and is less optimized. SQL is a declarative query language, whereas IMS and Codicil query the database using imperative code. Most programming languages are imperative. For example, if you have a list of animal species and you would like to return only the sharks in the list, you would write something like this. Now in the relational algebra, you would instead write this. So when SQL was defined, it followed the structure of the relational algebra fairly closely. So, an imperative language tells the computer to perform certain operations in a certain order. For example, you're telling it here to start a for loop and then perform the if condition to filter out the sharks and then return the sharks. Whereas in a declarative query language like SQL or relational algebra, You just specify the pattern of the data you want, what conditions results must meet, and how you want the data to be transferred, but not how to achieve that goal. It is up to the database system's query optimizer to decide which indexes and which joins methods to use and in which order to execute various parts of the query. So, a declarative query language hides the implementation details of the database engine, which makes it possible for the database system to introduce performance improvements without requiring any change to the queries. Also, declarative languages often lend themselves to parallel execution. Imperative code is very hard to parallelize across multiple CPU cores and machines because it specifies instructions that must be performed in certain order. Declarative query languages have a better chance of getting faster in parallel executions because they specify only the pattern of the results and not the algorithm. The database is free to use a parallel implementation of the query language.